So water can dissolve many, but not all, ionic compounds. Now let's see exactly why that would be. And for that, let's get a couple of examples up here. Now, ionic compounds are the cases where we have ions being held together by charges, and we call that an electrostatic interaction. Now, they might dissolve and dissociate, but we have to see. So we have to ask ourselves, are the water molecules going to be pulling hard enough? Now, notice that in NaCl, what we have is a -1 charge and a +1 charge. And they're sticking to each other. So they're sticking to each other quite well. Actually, the stickiness of a full-size charge to a full-size charge is actually going to be stronger than most single covalent bonds, which is actually a little bit surprising to us when we say, oh, NaCl, of course that dissolves in water. What do you mean, of course? That's like saying, oh, molecules, of course they completely just fall apart into atoms in water. That doesn't make sense to us. After all, water itself has covalent bonds, right? They don't just fall apart. Covalent bonds are strong. If these are even stronger, why are they falling apart? And for that, we have to remember what's really going on here. Remember, if the green ones are the chlorides, we're going to have a water molecule shaped kind of like this. We'll have our hydrogens at the end. I'm just going to draw it as this boomerang for quick simplicity's sake. That means that this side is going to have that partial positive charge and stick to it. This side's going to have a partial negative charge and be sticking, well, to an Na plus instead, or just out into the solution. Now, if we have 2 or 3 of these water molecules, though, and remember, they can approach in 3 dimensions. So there could be one kind of here in the foreground. Let me see if I can scribble it right on top. Right here. We could have another one over here, kind of in the back, trying to grab it. Another couple over here, trying to grab it. If there's enough of these water molecules sticking to it with that partial positive charge approaching that partial negative charge, it may actually stick enough to help pop them loose. I like to call this kind of my ants on crack model of salvation. If you're picturing a bunch of those giant radioactive ants from a 1960s horror movie, when they come over and they try to grab the crowd of people holding on to each other as tight as they can so they don't get dragged off to the ant nest, what has to happen? The ant needs to pull it away from the human that's holding that human on, right? So you're both holding like this. You're trying not to be pulled away by the ants. So what happens? 2 or 3 ants start pulling on you. If those ants are able to tug strongly enough, off you go to the ant nest. However, if they can't coordinate and pull you loose tightly enough, then you're going to manage to survive the ant raid, and you're going to stay sticking to all of your neighbors, and all of you humans get to survive. Now, how does that ridiculous model connect to what we just are looking at right here? Now, NaCl, +1 and -1 charge on these two, right? How about calcium carbonate, chalk? If I drop a chunk of chalk into water, it's not going to dissolve. At least not right away, right? Because it's got a +2 sticking to a -2. That makes it harder for it to be dissolved and dissociated. And that means it's less likely to pop loose. The water molecules can't coordinate to pull tightly enough. Now, if I heat it up, I can probably get the calcium carbonate to start dissolving. That happens in your hot water tank. But maybe it won't. It all depends on what exactly the ions are and some of the other forces that will be at play. Now, molecules, though. Molecules have those strong covalent bonds, which I pointed out aren't actually as strong as these ion attractions. But because of the way that they work, it becomes very difficult to break any of them. About the only one that will break is an H. You can break an H plus off of some molecule, and those are going to be ones that are super stable and have good resonance structures and things once you pop it loose. And those are typically going to be those ions that we had to memorize, the polyatomic ions that can be negatively charged. Most of those will make good acids. And so we'll be able to have a hydrogen on there that can pop loose as an H+. But even then, most molecules can't do that at all. Acids are about the only exception to it. Now, here's a quick checkpoint, though. I want you to just pick which of these two would be drawn correctly if you're thinking about a water molecule. Okay, well, let's take a look. We know that this is the O. These are H's. Oxygen is way more electronegative. If it's more electronegative, that means it's going to get the partial negative charge on this side. partial positive charge on that side. And this negative charge is going to be repelled by this. So answer B can't be the correct answer. It would have to be answer A. So things are going to line up like that. And remember that I'm showing it in 2 dimensions, but reality is 3D. So make sure that you're thinking of this as being surrounded by an entire swarm of these ions. This is what that's going to look like in solution. Again, they've flattened it out a little bit in this artwork so you can see it. You can see there's 6 water molecules coordinating in a single plane. But if you're picturing the ones in the front and the back of the molecule too, this negative ion is probably being held up by somewhere between 10 and 20 different molecules of water, right? And for an even bigger ion, it might be more. It might even get more to stick if it was a +2 or a -2. It's going to depend on a lot of factors. It's how many water molecules does it need to keep it dissolved? But let me also point out then, we can also run out of water molecules. You know what that's called? That's called a saturated solution. So when things are saturated, when you've run out of water molecules to keep the 2 ions apart. That's what's going on when water tries to dissolve an ionic compound.